Welcome to the first episode of PowerPoint Weekly, a series aimed to familiarize scientific theories, models, results of recent publications, and some milestones in science. And today, we'll cover a brief background and motivation behind one of my research areas, Cavity Optomechanics. Pioneered by Braginski in the late 1960s, over the years, this area has found many applications in the nano, micro, as well as macroscopic domain. So, without further ado, let's begin. Optomechanical systems, which study the interplay of light and matter, comprise a wide range of devices, but typically they can be modeled as laser-driven cavities consisting of movable end mirrors with mechanical resonances and optomechanical coupling rates in the order of megahertz and kilohertz respectively. The first image here shows an end mirror with alternating dielectric stacks placed on a silicon nitride mechanical oscillator. Other configurations include, but are not limited to, whispering gallery mode mechanical oscillators, microring resonators coupled to waveguides, Fabry-Perot microresonators in single-mode fibers, etc. Thanks to the advanced nanofabrication techniques, optomechanical systems are now being used to answer some fundamental questions of quantum physics, study higher-order nonlinear effects and radiation pressure-induced noises, as well as explore new physics such as those pertaining to dark matter or quantum gravity. Their integrability with solid-state devices are contributing towards the era of quantum computers via novel, hybrid, on-chip architectures. Also, since mechanical decays are significantly lower than optical ones, such devices can be used to store optical information in mechanical modes, thus acting as memories. Further, mechanical oscillators in such devices can also mediate the transfer of optical energy to other forms, making them a great candidate for transducers and buses. Finally, the tunability of optomechanical systems help achieve extremely sensitive measurements, such as mechanical sensing in the attometer or zeptonewton scale, or detecting gravitational waves using kilogram scale movable end mirrors in optical interferometers. However, due to intensity fluctuations of the laser drive, a shot noise is introduced into the system. Also, the radiation pressure interaction adds a back-action noise. Together, they limit the minimum phase noise that can be achieved in a cavity optomechanical system, which in turn affects measurements. To overcome this constraint as well as to leverage some additional benefits, hybrid systems comprising of optomechanical elements coupled to spin states, charge states, electrical elements, as well as superconducting qubits have been studied extensively in the past decade. But that's a topic for another day. Until then, stay tuned.